Good evening, everyone. I hope the stream is running, and welcome to the part 2 of Task 1's live stream. So yesterday you guys had a brief, like you guys went through the ROS environment, had a look at Gazebo, had a look at all the packages, got a nice tour of the setup. Now I think it's time for us to start the actual coding, right? Let's get into the script part of the challenge. So with no further delay, I think it's time for the presentation. So let's just open the presentation. And also, I would like to know if everything's running well by giving thumbs up in the chat, so I get some feedback from you guys. Uh, Also, along with me, we have here Vishal and Sahil and Sufyan. So they will also be helping me out with the stream, and they'll probably answer some of your questions in the chat as well. So yeah, okay, I'm seeing some thumbs up, and let's begin. So today we have the main topic for the day, as I mentioned already, is the controller.py. So we'll be focusing only on the concepts of controller.py. We'll not be actually writing the entire script for you, because then there's no challenge for you left, right? So in the concepts, it's like the building blocks are given to you. You'll have to actually make the construction, right? So let's go through some of the building blocks. But I think before we do that, it'll be a good idea to go through the objectives, just to revise ourselves, to get us all on the same level ground. I hope you guys have gone through the mdbook already. At least once you might have skimmed it by now. And if so, all this will be very familiar. You already know the objective very well, that the controller.py .py file has to create a node. The node's name is going to be ebot controller, and it has to subscribe and publish to a few topics. It has to subscribe to two sensor topics. One is the ODOM and one is the laser scan, and it has to publish to the CMD well to actually control the robot, right? We'll have a little closer look at all these things in the coming slide. And the execution of the actual logic and the controller, right? That is the exciting bit. So once again, I just want to stress over here that we are going through the mdbook in a sense, but it's no way a replacement for the mdbook. Again, go to the mdbook. Don't think of this as a substitute for the mdbook. It's only a book. So in. So the first section, I've kind of divided this presentation into two sections. One is the ROS side of things. How do you interface your Python file with the ROS environment? By interface, I basically mean how do you create the node, talk to the topic, send messages, receive messages, all that kind of stuff. And the second section is going to be the algorithm side of things, where you'll actually write your logic and the algorithm to solve the problem. So first we'll begin with the ROS side of things. All this you might have already come across in the mdbook, but I'll just add a few points that you might find useful while you do all these things. That's why the video stream, to add a few things that you might have missed in the mdbook. So creating the package, that is already been mentioned, that this is the kind of structure that you will get once you create your package. We have left the creation of ebot controller for you, so you're comfortable creating packages and doing it all from scratch, right? At least the controller package. And while creating the package, obviously, one thing that you'll have to remember are the dependencies. So if you use the catkin create package, you'll be mentioning dependencies, right? So in those dependencies, you'll be mentioning quite a few things. For example, ROS.py and all the message types. And if you're curious what happens when you mention all that dependencies, once the package is created, you'll see the package .xml file, right? So if you go to that, you'll see these lines that are added for every dependency that you have added. So if you're curious, you can just have a look at it and make sure these lines are there. That means you have added all these dependencies for nav messages, nav message for the odometry, geometry message for the twist message. Standard messages are always used for a few things, ROS-PY, ROS-CPP, all those standard things. So yeah, that is about the packages. And once again, just to mention again, make sure you follow the naming convention, the naming as given over here. Make sure you name the package exactly that. Make sure you have the script file and the Python file inside the script file as shown. That is very essential for evaluation point of view. So that's the last note on packages. Messages. So if you see the important import section, there you will see there are a few imports that are relevant to the messages side of things, to send messages and receive messages of a certain type. And if you're curious, again, in the mdbook, you would have seen the links to all the messages documentation. So all these are nothing but simple things put together to make something more useful. So for example, if you look at twist message, this is what you'll see in that link. In that, it's basically nothing but two vectors, one for linear and one for angular, and that's the naming that they have given. And if you go further into what is there inside vector 3, you will see there is x, y, and z. So that rhymed. If you see what's vector 3, it's x, y, and z. And in linear xyz, there's angular xyz. And if you further go into the script in the mdbook as well, you'll notice in this slide, I've actually had few lines here. In velocity message dot linear dot x, that is what has the forward velocity, and angular dot z, that is what has the angular velocity stored. So that's the structure that we'll be using for that's therefore this import. Similarly, you can go through the laser scan and odometry. The links have been provided there. You'll see the structure for yeah, laser scan. You'll notice the ranges float array, and you'll also notice in odometry there is pose and twist and all that. So observe that and notice where it comes into the code and why it's all like, just instead of following it blindly, right? So that's about the messages, some of the important imports, right? And now coming to the main heart of the program, the control loop function. That is where you initialize the node. That is where you create the publishers, subscribers. Uh, Obviously, it's pretty intuitive as soon as you read the line that you're initiating the publisher and subscriber there. The rate, as mentioned in the mdbook, make sure that the while loop, the main controller, runs at a fixed rate along with the wait.sleep command. And you'll see the velocity underscore message is of twist type. And as mentioned earlier, you have the x and z to actually control the linear velocity and the omega. So if you notice here, we have two variables to define the motion. One is linear velocity and one is omega, right? V and omega. And if you want to get technical, the actual term for this is unicycle. Unicycle model is controlled with just these two variables, V and omega. But if you're familiar with differential drive, you would know that that's not how you control it, right? When you actually write your final control, what are the two variables that you use when you actually want to control the robot? Could you guys put it in the chat? This V and omega, you can't give it to the final embedded system, right? You'll have to give something else, two different variables. What are those? Would you like to mention in the chat? I'll wait for that. In fact, I'll not wait for that. I'll just say it out. Hopefully, you guys are responding to that question. It's basically VL and VR. But luckily for us, you don't have to do that conversion. There is a URDF file, as mentioned yesterday. I hope it has been covered. That it does all that for you. So anyway, skimming through that. Here, I just wanted to mention one thing before we go on and write our algorithm. That is, here you can just give in two velocities, give a linear velocity of certain constant, give an angular velocity of certain other constant, and see what happens. Just run the entire script. Obviously, what does that mean? What is the path that the bot will follow? You guys can again mention in the chat just to get some to see that you guys are responding. Yeah, VLVR. Okay, great. So, and also there's a 20-second lag, so I'll not be getting the response immediately, but about this also you can mention in the chat. So it'll be following the circle, right? So make sure you do that. actually write two values and see what happens when you run the script. Don't even need to start writing the algorithm. Why do I say that? Because the next slide, actually, I'll skip this slide for a second. The next slide was going to be about ROS run, ROS node, ROS topic, and RQT graph. Especially ROS node, ROS topic, and RQT graph. These are the three commands that you have to be familiar with. You have to explore them. You have to understand. If you want to understand what nodes and topics and what are the connections that are there between them, the RQT graph is extremely useful. So this is why I wanted to say that. Just do these two things. Make sure it runs in a circle and see what's happening behind the scenes using these particular commands. ROS run is obviously for just running the Python script, but the other three commands. Right, so that is all for that. There's one more part of this code that I maybe thought should be highlighted a little bit because it may not be very obvious why it's all like that, which is the laser callback. If you go to the mdbook, you'll notice there's a certain callback function. In fact, in this script, you'll see there's a subscriber, and in the subscriber, you also mention a callback function. And the callback function's name is given here, which is laser callback. And if you look at laser callback function in the template, we have provided something like this, but it may not make a lot of sense. You might be familiar with the ultrasonic sensors where you put probably 5 ultrasonic sensors all around it, and you'll just get one distance values for each of them. That's the kind of thing we want to simulate here, but instead of just giving off the ultrasonic sensors, we have given a laser scanner because it's a cool sensor, right? You might want to play around with that. And we'll actually create an ultrasonic model out of that in one sense, which is you'll have this is also very flexible. Here in this example, we have given 5: back right, back left, front right, front left, and front. So you'll set certain range of angles that you want to see. So the laser scanner will be divided into 5 chunks in this particular example. You'll look at this chunk, find the minimum of those values, and that will be your front reading. So now you have a lot of flexibility to decide which range you want to look at. You need not look at only if you have 720 readings, that's a lot of data, right? What will you make sense out of it? It's a lot easier to have 3 sensor values that you want to manage. So you can, or 5 in this example. So that is what this particular callback is going to do. It's going to divide it into regions and take one value out of each of those regions. And that one value usually makes sense if it is the minimum value, right? The closest point that you're seeing in that range. And in the example, you would see min. I think it's in the later half of just following this code where it's written min, and one example code has been given to you where you could use that, for example. And I think if there are any more questions related to this, you can put it in the chat and we'll cover it. So yeah, I think with that, we'll move on and come to the main highlight of the session today, which is the algorithm. So in the algorithms, again, we are only covering the building blocks of the algorithm. We are not actually going to discuss the actual algorithm, but the building blocks will help you in some sense. So that's why I'll cover it here. So this is the challenge, as you already know. Waypoints. So you have seen the function called waypoints, and if the keyword is not the word is not very familiar to you, waypoints, it's just if the final goal is certain point. So in this case, I guess this would be the end goal. There are intermediate goals that you want to achieve, right? So those intermediate goals is what we call waypoint. That's all. So if you want to cover this particular curve, you'll break it into certain waypoints, right? So in this example, you'll see 10 waypoints. You'll see 1, 2, 3, 4, 5, 10 waypoints over here. That entire sine wave is broken into 10 waypoints. But why 10? You could choose a different value. And just to mess around with the thing, I've just plotted the sin x by 2 multiplied by 2 function here. And if you change n, you'll see that the number of points get packed tighter and tighter. I've only shown the first 10 waypoints. Obviously, it's going to continue all the way to 2 pi. I'm pointing at the screen, but you guys will not see me pointing at the screen. But the point is, first 10 waypoints are shown from here to there. And as you see, as you increase the number of waypoints, you'll get a higher resolution. But yeah, you'll notice some compromises that you'll make with higher resolution and certain compromises that you'll make with too low a resolution. So if you go with just 3 waypoints, you'll get a triangle wave and it might be not so good for you. So deciding what the resolution should be is another fun thing that you can mess around with and figure out. So that's about waypoints. So now one thing is clear, that whether it's tracking the sine curve or going to the final destination of 12.5, 0, either way, you'll need some controller to achieve that, right? And that is going to be something like a go to goal controller. I just named it like that, go to goal controller. So your robot will have, I hope you guys are paying special attention to this section, because this particular slide will be extremely helpful for you. It's almost like a cheat code in some sense, but there's a pseudo code. You guys will have to do the work on it. But we've kind of explained how you can go to goal. So this is one of the approaches. There are multiple approaches. I've explained one of the approaches. So you have a robots x1, y1, and you have a theta ebot underscore theta. So these are the three things that you have in your pose. That is x1, y1, and the heading that the bot has right now. And what do you want to achieve at the end of it? You want to achieve certain x2, y2. That could either be 12.5, 0, which is your end objective, or it could be one of these waypoints that you just prepared. So you have an x2, y2, and you want the bot to reach x2, y2. What would you do? One of the approaches would obviously be go correct the theta error, right? You have an error that is created. Your bot is heading somewhere, but the goal is somewhere else. There's a particular angular error, right? That would be called e theta in this particular pseudocode. And that e theta is nothing but theta of the present bot minus the theta of the goal. And what is your objective? You want to make that e theta 0, because then you'll be looking straight at the goal, right? So making e theta 0 would be one approach. You just make e theta 0 at the same spot, keeping velocity 0, and then you start heading towards the goal is one approach. But the other, a simpler approach that I prefer, and I think is what many people prefer, is just to have a constant velocity. You give a forward velocity of certain constant. Here I've shown v and omega. So v will be certain constant that you can decide, and omega is going to be proportionally reacting to your error. So this kind of, just by reading it, it should kind of make sense to you. So if the error is bigger, you get bigger reactions to the omega. If the error is smaller, you give smaller reactions. So that's what is a P controller, right? There's a much bigger story to this entire thing, which is the PID controller, which is not very essential to complete this task. So therefore, we have not covered it here. But if you're curious, there's a lot of resources on that you can always explore, which is second and third element of the same controller, PID. This is the first element, and this is a very natural controller that you'll come up with as soon as you want to control, you want to reduce the error. How much time do we have? Okay, we have covered quite a bit. We're almost towards the end, so we'll be able to cover it. So yeah, if you just do this particular thing, there is a bit of tuning that you'll have to do. So imagine what happens if you have very low p-value and very high velocity. It will just circle around the goal is what will happen, right? If you start thinking about it, you'll realize why. If you have too high a velocity, it will not be able to correct the theta quickly enough, and you'll just start circling the goal. And if you have too high a p and too low a velocity, you'll start oscillating towards the goal. Instead of going straight to the goal, you'll start going crooked towards the goal, right? So that's a bit of playing around that you'll have to do. But yeah, that kind of summarizes this particular controller. And there's a very good resource that I would recommend, I guess, for this. In fact, there's an animation of all the things that I just described. I'll probably put the link in the description, which is a Coursera course on mobile robotics. So in that, they've kind of they've explained the same concepts in a good detail. So there's particular one video in that entire series that is very relevant here. So yeah, I think with that, we'll move to the final few slides. Bug algorithm. This is something that, this is a keyword that we just wanted to throw at you and let you guys do all the exploring. Bug algorithm is a pretty useful kind of thing that you would want in this particular task. We will not go into this in any detail so that you have some exploring to do, and we don't end up giving the entire task away over here. So bug algorithm is something for you to explore, and we'll leave it at that. No more of bug algorithm here. And finally, there is this interesting topic of quaternions and Euler. This has been mentioned in the MD book, and for the people who are curious, there is a lot to explore over here. And there's one video that I would very strongly recommend for those who are very curious and eager to learn and are willing to put in the effort to learn it, because it's quite some effort, and even I have to go through that again to actually revise it. So there's the Three Blue One Brown channel by Grant, and he explains this topic extremely well with animations and all that. So yeah, that is a very good resource for you. And finally, just to conclude this entire thing, I'm bringing back the thing that we explained in our very first session, which is the rubber duck debugging, right? Always make sure you sit with the team and try to solve these problems, because sit with the team or even explain what you have created to the team. So as soon as you start explaining, you not only get better algorithms, you get even your debugging becomes faster if you have any issues. So just thought of mentioning that again before we wrap up. With that, I think we can conclude our session and not the session, conclude our presentation. And I think we can go to the question answer session if there's any questions in the chat. Yeah, so I think I'll stop sharing now. And we'll have a look at some questions from the chat if there are any.
Yeah, they're not much. Let's just wait for a few more minutes.
Yeah, sure. I've seen people requesting for the links, so I'm just putting it in the description. It will be shown in the description very soon. Um, I think it's best if we edit the description at the end of the stream, so you can check it at the end of the stream. So yeah. Saurav, like the sidewall is just a decoration. It's not really meant to be tracked. So that is not something for you to actually track or sense. That is just there for decoration. The sidewall, I hope you mean the sine wave. The sine wave is not something that you have to track. You just have to use the odometry to know where the board is. So the odom is going to give you the pose of the robot. It will give you the x1, y1, and theta of the robot, and you use that to control it further.
Okay, so I
Um,
think he's confused with the walls and the wavepoint. So those lines basically, what Arjun has said, is the diagrammatical representation of the path which you are supposed to have. But the path that needs to be followed has to be defined by you in your Python script. Your Python script should generate that path, should sample that path, meaning it should like from the presentation, like Arjun said, the curve path would have some points, some sample points. It should reach those points first, and while doing so, reach one point, then next point, and then the next point. While doing so, should follow the same path as described in the world. Okay, so you don't have to actually wall follow, but you have supposed to compute a equation, remove points, and then go to those points.
Regarding evaluation, there is a question that if you touch the walls, are there going to be deductions? So on that, I think the only point to mention is the further away you deviate from the curve that has been given, the greater the error, right? So that is how the score will be defined. But I think that should be your final concerns list. So if you have a concerns list, your concern should be first to complete the task and then to complete the task in better performance and reduce the error, do it faster, all that kind of stuff. So you can focus first on just completing the task, and once you're done with that, you can come back to reducing the error, the deviation from the path that you need to follow. So yeah.
Ibrahim, and then yeah, we know we have given too much of a hint this time. So we had decided we won't be giving that much hint, but seeing some of the responses of on Piazza made us realize that we need to convey our message more properly. People don't normally go through a documentation even though everything is provided. But if there's a video, if you verbally explain it to them, they might know the problem statement. Also, yeah, don't worry, we won't be sharing much information, much hint in the next task. The next task will be much more difficult, 10 times difficult than what it is. And yeah, and the later task would be 100 times more difficult than what it is right now. So providing hint won't be possible from our side also. We have the solution, but what's the point of having us giving a solution or hints if this is a competition?
Shubhangi has asked what is P and the P into E theta. So as Ujjwal has answered in the chat, it's a proportionality constant. So it is how quickly you will react to the error. So if you have a certain error, the P is your multiplication factor, right? If you just keep 1, it would mean you react with 1 into E theta. And if you keep increasing P, it's going to just react that much more vigorously. So if you have a certain error and you have a huge proportionality constant, even for small errors, it's going to react abruptly with huge forces. But if you have a very low P, then even huge errors, it's going to give very slow push towards the center. So that kind of defines how much push you get towards the center, uh, the P value.
Okay, Saurabh, you don't actually have to map the obstacle over here. So, if I'm correcting, if I'm assuming the question correct, the sensor, the laser scanner is for you to get familiarized with right now. Its purpose will be used later on, whatever mapping and all to be used later on. Right now, what we want you to understand is how to use those information, to use that information and etc. etc. So right now you have to use it to see if there's an obstacle or not. That's it. Not for this task mode one doesn't require it for mapping anything. Arjun, does that answer his question? Can you read the question also?
Um, oh, sorry, I missed which question are you referring to?
Saurav Layak's question.
Oh, okay. That's previously. Oh, okay. Mapping, yeah, mapping is not part of this challenge anyway. So I guess the word mapping itself is not for this task. It's you could explore that, but it's not used in this particular task. So yeah.
Okay, so
Uh,
someone is asking how to get past the concave wall. So like a single word for this bug algorithm, simplest one actually. Search the internet about bug algorithm. There are three types. Search them, select yours, and implement them. You will get abundant resources on the internet. That's the reason why we are not explicitly mentioning it or explaining it. Okay.
P is empirically assigned is the question there, and yeah, P is kind of experimentally decided. You'll have to figure out that by actually tuning it. So yeah, it's kind of a fun little experiment that you keep doing when you first time do it. But yeah, you'll get a hang of it as soon as you start. It's not too difficult to tune just P. But yeah, when you do get into PID for any for further interest or just for exploration, that is where tuning is going to be a lot more uh, fun and challenging to explore. So right now it's a pretty simple task of deciding what P should be. Yeah, but it is experimental. So yeah.
Next question is it possible that there is a delay in the simulation when we command turtle to stop? Okay, so this is respect to task zero. Okay, so turtle sim bot, I don't think so there's any delay. Okay, it's pretty much the delay would be around in milliseconds. I mean, I'm not even sure. I think it would be even less than that. So If you're asking this with respect to gazebo, then it's a good question. So if yesterday Sahil mentioned about a real-time factor, so yeah, if your real-time factor is less than 0.5, you can actually see a delay. So the moment you press command, it will take few seconds, very less second, and then you can see that command being executed. But that is the case when the real-time factor is very less. Okay. Most of the cases, the communication is very fast. Inside TCP/IP protocol is used. You can go on the internet. You can look inside how the communication inside ROS and Gazebo works. It's quite fast. You don't have to worry about delay and all, unless and until you have defined it yourself inside in your Python script, of course.
Since we have two questions both on P controller, I just thought of sharing this particular GIF over here. You guys can go have a look at it. Once you have explored PID, then it will make a lot more sense. But this particular GIF is a very good GIF that explains PID in like a nice, beautiful summary. So it will not be probably very effective if I start explaining what this thing is doing right now. But if you notice, initially both I and D are set to 0 and only P is increasing. And if you notice what is happening to this blue curve as P increases, the red line is the set point. You want to try and reach that set point. That is where E theta, your error towards the goal, is going to be 0. In our case, this will be 0 E theta. And initially, you'll be at a certain huge error, right? You'll be facing somewhere else completely. And your objective is to make E theta come to 0. And you can observe here how quickly, how smoothly, how bouncily it's coming to 0, right? So that's the effect of PID on that. This system, it will depend on what system you're trying to model. So this might be defined for a different kind of system. In our case, if you just use a P itself, it will come to the thing pretty easily. So that's why we don't have to explore I and D. It will reach the set point conveniently. But yeah, this is just an added resource for you to explore. Oh, there was one important point that I had written in the slide, but I forgot to mention. And I think I should probably share the screen again because it's a very important point. And I hope you guys don't forget this when you're designing your thing. And that is when you work with angles, it's very important to make sure that they're in the right range because angles are looping forever, right? You get 0 to 2 pi, 4 pi, 6 pi, you can keep going forever. Same in the negative direction. But if you have a P controller and you're supposed to react the same way if it is 2 pi or 4 pi or 6 pi, and instead if you react double the velocity for the same angle, it doesn't make sense, right? So the norm is to always have minus pi to pi. So the greatest error will be pi. You're facing in the opposite direction. You need to go somewhere. If you're facing the opposite direction, you'll either be very close to pi or minus pi, depending on like slightly this side or that side. So 2 pi doesn't make sense, right? 2 pi is 0 basically. You're already heading the correct direction. You don't want to react to 2 pi error. The P controller will say, oh, 2 pi error, we need to fix that. And therefore it will react huge numbers. So that doesn't make sense. It should be
Yeah,
0, right? So,
Arjun, can you repeat that? Can you repeat about this again? Because I think there was a delay from your side.
oh, okay. Just to repeat the point again, the angles must be within minus pi to pi, and it shouldn't go beyond minus pi or beyond pi, because a perfect example would be, imagine you have an error, e theta error is 2 pi. What does that mean? Your error is 0 basically, right? You're already in the correct direction. You have just rotated one entire round and looked back at the same direction. So if your error is 2 pi, what should be your reaction? Your P controller should say 0, right? It should not try and correct something because it's already in the correct heading. And therefore, 2 pi error doesn't make sense. It should be 0. And therefore, it should be within minus pi to pi. And what does pi and minus pi mean? You're facing the opposite direction. If your heading is supposed to be somewhere and you have a pi error, you're looking in the opposite direction, right? So that is the worst case scenario. So the error can't go beyond pi or beyond minus pi because there's not like it doesn't make sense, right? So that's an important point that I had to highlight again before we leave. So yeah.
Yeah, I think we have said more than enough for the. We have given more than enough for the hint for the task. By the way, Gaurav Singh Bhati, yeah, to answer your question, which you have posted thrice, same question, okay? No, the small error in Turtle's task won't be deciding factor. Task zero was basically to complete a single circle, that's it. So you don't have to worry that much. Objective, yes, that was the objective, but it would be evaluated, okay? So I don't think so there are any important questions left. Actually, there's no question left as such.
Yeah.
So in 4 minutes, I think we'll at 4:45 we'll close this session. Okay.
Also, on the same point that was already mentioned about minus pi to pi, there's a function called 8 and 2 in math, which is going to be very helpful. So you can Google what is 8 and 2. Um, just another point that had to be mentioned. Okay, so
So weightage of all the tasks, no, it's no, it won't be the same. And what it would be is we cannot reveal that. Okay. We It's our discretion, so we cannot actually reveal that. Arjun Gupta, you haven't actually cannot see your question. If you can post it again, that would be nice.
also, uh, I would personally not worry too much about the weightage and the scoring system. I would personally rather focus on just completing the tasks. I think as long as you keep completing the tasks with just bare minimum as well, you'll keep making progress, right? So I think the focus should be more on that and not worry too much about this because we're all friendly people. We'll not chase you away because you did something you did a minor error or something. So yeah, the focus should be on completing the tasks as well as you can.
Okay, so Darshan Patil, yeah, I think someone has answered your question. So I think Arjun, that's it. I think so.
Yeah,
We should come. Yeah, we should commence this session. Okay. If you guys have
sounds
any
good.
more doubts, genuine doubts, okay, just post it on Piazza. Of course, you can also post other doubts, but make sure that you go through Piazza before posting, or and especially go through Google before posting. Most of the doubts are already available. Solutions are already available on the internet. All you need to do is just search them and spend some time. Okay, so that's it, guys. Thank you very much for coming. Bye bye.
Also, for the next session, we would recommend you guys to call your teammates as well, in case you're the only one from your team who is present for this session. I'm wondering why only 75 teams have taken interest to come to this session. So, anyway, feedback would be appreciated wherever on Piazza or in the chat. So, yeah, thanks.
Arjun, there is one more question. What to Euler file? So, yeah.
So yeah, the point is about Quaternion and Euler. As I mentioned, that's a pretty deep topic to explore. But whatever is required for completing the task is already mentioned in the mdbook. You just need to call that function and use that basically. For if you don't care about what the actual stuff is, even with just the thing that has been given in the mdbook, you'll be able to survive this task one. But I would highly suggest you go through those
No, I
topics
think
and understand what
he's
they are.
asking whether is he supposed to make what to Euro
Oh,
file?
separate file. Oh,
Yeah.
right. So I think there was one error in the mdbook when we released it, which is we have shown a separate Euler file, a .py file, which is not supposed to be there. You don't need a separate file for that. You just call those functions within your main controller.py file. In fact, we tell you not to create any file apart from controller.py. You don't need any other files for that. So yeah. Um, huh. I hope I think with that we can conclude this session, and we'll see you guys next time. Bye.